Hey, welcome back. We're going to get started with session 2, where we're going to cover the single particle cryo-ET processing pipeline in nextPYP. The first thing that we're going to tell you about is pre-processing of tilt series. So how we're going to define pre-processing here is starting from raw data and going through particle picking. So pre-processing of even a single tilt series is relatively complex. You need to collect your raw data, go through motion correction, tilt series alignment, CTF estimation, tomogram reconstruction, and finally on to particle picking before you can take those particles off to refinement. We show here an example of some of the softwares that people commonly use for those. Some of these are incorporated in nextPYP, but the point here is that there's a lot of options. You can hop in and out of things, and it can get pretty complicated as you need to download and transfer data between programs, which is kind of the rationale for a pipeline. As you've seen with other Cryo-ET pipelines, we like to keep things in one place. But when you think about trying to do this for hundreds of tilt series, which you need if you want to achieve high resolution structures from tomography data, this kind of becomes unmanageable. It's huge data amounts, it's a lot of moving around, and it's just kind of scary. So this is why we try to automate this process as much as possible. So we have on the left here, where you can see our two blocks, our import from raw data block and our pre-processing block. Those are going to be covered in this session now, and then things to the right are for refinement, and that'll be covered in the next session by Shunfu. But as you can see, there's only two blocks required, which is pretty condensed for a pre-processing pipeline, and it allows you to start your pre-processing run, get things going, and get it moving all in one go. You don't need to go in and out of different things, start new jobs, all that. You can just start one, let it go, come back, and you're done with pre-processing. So first we're going to cover our data import block, which as you saw in that previous slide is a separate block from the pre-processing block. The reason we separate this out is to have a lightweight data import block. So lightweight being is you're just looking at a couple of images. You're not doing any heavy processing. All you're going to be doing is applying the gain reference. And then you're going to see one single random image from your tilt series coming up in this thumbnail. And you can use this to visualize if your gain reference is applied correctly. Like if it were applied incorrectly, you might be seeing things like lines or like artifacts that you don't expect to see if you've correctly applied your gain reference. So this is done prior to pre-processing in that first block. We have a few options for this block. Here is what will pop up when you first hit import data. You can do single particle, but as we've mentioned before, we're going to be talking about tomography during this webinar. And the feature that we're going to be demonstrating is going to be importing tomography from raw data. However, you can also import tomography from STAR, from other PYP projects, or from sessions, and you'll see sessions covered later as well. For file types, we're going to support your typical like MRC, TIFF files, your DM4 files, and then also the newer camera files, the EER files as well. So pre-processing, we choose to do this in a single super block, and this is to help automate things, keep things faster, help you to visualize all your relevant pre-processing results in one interface. And we do this here. You can see how you set the parameters. You have your alignments, your CTF determination, tomogram reconstruction, various tabs that are applicable for different types of particle picking, and a subtomogram extraction if you want to do that. And then finally, your resource allocation tab, all in one panel, easily clicked through in the web interface. So the reasons that we use a super block, again, it's automated, it's faster. All the pre-processing steps are easily accessed in one place, can visualize all your results in one place. And one thing we would point out is that when you update parameters, it's only going to rerun downstream steps. So say I want to change my searchable to focus range, it's going to keep my alignment and save that, and it's not going to update it or rerun it. It's just going to rerun CTF, reconstruction, particle picking. Or say I'm happy with my reconstruction and I want to change my particle picking method, and I do that and then I run the block, it's only going to update the particle picking and it'll leave the prior steps alone. This is to help things run faster. You're not wasting time rerunning things you don't need to, but it can still keep it condensed in that super block format. So the first step in our pre-processing block is tilt frame alignment. Frame alignment is when you're taking multiple images at each tilt and you need to align those frames. It helps you to get a better image than if you only have one image taken at each tilt. But this can take a lot of time. If you say you take 5 images per tilt and you got to align all those 41 times for 41 tilts in a series. But we do this and we have a nice graphical user interface for visualizing the results for this. So the way we do this is we default to using unblur, but as been mentioned before, we now support Motion Core 3 as well. But you can visualize the results in the interface here. So you have your tilt axis angle on this axis here, and the average motion in pixels on the y-axis. And you can see this looks kind of typical for what you would expect of a successful alignment where you have less motion at lower tilts and more motion at higher tilts. You can also see your tilt axis angle estimation and on a image of that tilt image. And then you can get a motion trajectory for each tilt angle. And these plots here will change as you scroll over here, but you'll see that more in the practical tomorrow. Some critical parameters that we're going to recommend you look at when you're doing frame alignment is first, if you have single file tilt series, you should check this option. So know what format your data is in, that way you can enter it properly. And along those lines, the frame pattern as well. We put it this way, that way you can put information about your files in the name of your file and nextPYP can read it. And then you don't need to necessarily have MDoc files, but if you do choose to have those, you can do that. And then finally, alignment method, whether you're using unblur or Motion Core 3, you should have that selected. Next, after you do frame alignment, you're going to do tilt series alignment. So the options for that are fiducial-based or patch-based. Fiducial-based is generally better performance and faster than patch-based, but the benefit to patch-based alignment is that it's usable on any sample type. For example, on in-situ samples and lamella, you're not going to be able to get these gold fiducial beads into your sample, so you'll need to do patch-based alignment. And along those lines, we support iMod for fiducial-based alignment or patch-based alignment, and then we also recently added by user request our Tomo for patch-based alignment. And this is the GUI for visualizing your tilt series alignment results. This you'll see in the practical, but is a nice movie that you can play at various speeds and visualize your results here, and then your motion trajectory as well. Additionally, if you don't want to scroll through each thing, you can view all of the tilts alignments in one page. And that's pretty useful if you want to just get an overview of how well the tilt series is looking without needing to click through things repeatedly. And finally, tilt parameters. The one we would mainly consider is what method you want to use. So whichever method you select here, you'll get different parameters here that are applicable to that method, whether it's iMod fiducials, iMod patch-based, or Artomo patch-based method. After that, you would move on to your CTF determination tab in your pre-processing block. And CTF determination is a bit challenging in tomography. It's the nature of tilted specimens. There's a defocus gradient across the specimen. Additionally, the low dose makes CTF estimation harder, and you need to defocus. You need to estimate your defocus on every tilt image in your series. So what we do is we use info from the tilt series alignment to help improve the robustness of this, and you can easily see the results of your CTF in your pre-processing block along with your alignment results and later reconstruction results. So here you can see our GUI for CTF determination. So this is a plot you should probably be familiar with. If you do EM or ET, your 2D CTF profile, you can see your TON rings come out here. And your 1D CTF, and you can see how well your radial average is matching with your estimated CTF easily in one page. This is similar to the alignment, where as you were to scroll over this, and you'll see this in the practical more, but as you were to scroll over this, it would change and you would see an update for every tilt angle along the x-axis. We have this plot so you can easily see a summary of your data. So you can see your defocus estimation for all your tilt angles, your CTF score, your estimated resolution, and your change in defocus for all of your tilt angles in this plot. And then again, you'll see this in the practical tomorrow, but we also enable a feature to be able to export these plots as SVGs. That way you don't need to be taking screenshots for all your data. And again, this is global stats. I'm going to show you this for 1D and 2D CTF. So this is your 1D. You can see all your tilt angles. You could easily see if one tilt angle is bad. Maybe you'll want to exclude that, show you that feature later. And your 2D CTF as well. So for CTF determination, some parameters that you might want to change if, say, you're having trouble with it. One might be your max resolution. Certain samples you can expect to have different max resolution. Like say you have a in situ eukaryotic sample, this is probably going to be a higher number than if you have a purified sample. And then your max defocus, this is going to be something that you should know from your data collection. So if you're collecting your own data, you know what target defocus you're going for. You should set this defocus range to be appropriate for that target defocus. And then if someone else is collecting your data, you need to communicate with them to make sure that this range is appropriate to cover your target defocus estimation. The next thing that you do in the pre-processing block is tomogram reconstruction. And I'm saying all of these in the step, but this is all happening in the block at once. You set it up to go and it runs, but we're just taking you through the tabs and the steps. So tomograms is you're going to be aligning your 2D tilts, and these that have been aligned are reconstructed into a 3D stack. The reconstruction packages that we employed are iMod, which uses weighted back projection, RTOMO2, which uses weighted back projection or SART, and then we have an option now to include Topaz for denoising. Here, as we mentioned before, we show heavily binned reconstructions in the web interface for visualization and for downstream particle picking, things like that. We include an option to erase gold fiducials from the tilt series. So see here on this raw tilt image from Empire 499, you can see the gold fiducials here, and using iMod, they've been erased. And then this is a short movie demonstrating the success where you can't see the fiducials in the movie anymore. All right, so for reconstruction, we have a few parameters here. It's also going to depend on which method for tomogram reconstruction you're using, but the ones that we would highlight are erase fiducials or not. So if you do have fiducials in your sample, you can elect to leave them in, but if you did want to erase them during reconstruction, we have that option. And additionally, your binning factor for reconstruction. So they're generally going to be binned, but how much binning you want to do, you can determine here. Finally, we're going to talk, well, finally for this step, and then we'll show you a couple special features of our pre-processing block, but finally for this pipeline of pre-processing, we're going to talk about particle picking. So cryo-electron tomography methods currently require to do your particle picking in 3D. So manual picking in 3D is time consuming and it's really not feasible for large data sets. So we try to move towards using automated methods and pick on heavily binned tomograms to save time and space. And after we've picked the particle picking, you'll see more in the next talk, but we use 2D projections for refinement. So the particle picking methods that we currently support are manual picking. This is pretty easy to do in the web interface. You can save multiple lists. You'll see more on this during the practical and a little bit in this presentation. Then we offer size-based picking, and this is best for globular proteins, and it's very fast and effective. Next is geometry-based picking. This targets virions and spike proteins, gag proteins, things on the surface of virions. And lastly, neural network-based picking, which should be applicable for any target that you can pick a good training set for. Manual particle picking features lists that allow easy organization. They're copyable in case you wanted to edit it, but still save your original list. You're not limited on the quantity. I picked about a 5,500 particle set for a small protein that I was trying to test the manual picking and work on. And you can use it for the manual picking like I did if you want to do that, or you can use it for more the intended use, which is to pick neural network-based training sets for using our neural network-based picking. But this is a movie on how the manual picking works. So first, you're going to click New and then name your particle list here, and you'll hit Create. And now you have this list, you can go ahead and pick on your tomogram. You'll see more in the practical, but you can also slide through the Z stack to pick more particles as well, not just on one slice. But that's as easy it is, very simple to do manual picking in the web interface. Size-based particle picking is our next feature. The only input required for this is a particle radius and margin of error. So say my average particle radius is 50 angstroms, but I want it to pick up things that are 40 to 60 angstroms. I need to give it that information so it knows what range to pick from. This is going to work best for globular targets, things of uniform size. You do have that wiggle room, but the more uniform size, probably the more accurate you're going to be. And then they should be abundant. So if you're looking at in situ, ideally ribosomes or purified samples, the size-based particle picking is going to work very well for. And this is a demonstration of a result of the auto picking. In nextPYP, our size-based picking is called auto in our drop-down menu, and it works in situ. So this is, again, Empire 10499, which is mycoplasma, and you can see the ribosomes picked here in green. And you can get a summary of how many particles you picked down here as well. So 450 particles picked automatically by our size-based picking, which is very nice. For size-based, again, those critical parameters are really all you need for input is your detection radius and your particle detection threshold. So how much wiggle room you want to allow around that detection radius. Next, we feature geometry-based particle picking. So the first step in this is going to be detecting virions here. So it'll locate each spot, and then it's going to segment those, like as shown here. So this would be an example of the segmentation results in your pre-processing block. You're able to select whichever segmentation threshold you think best matches your virion, and you can also visualize these surfaces. And then say you got a false positive, something that's not a virion, you would be able to select to exclude that here as well. This step is optional. You can just go ahead and do your spike or gag or whatever particle picking you want to do, then filter out bad particles later on. But if you do the segmentation filtering before you do your particle picking, it can enable you to weed out some of those bad particle picking spots earlier on and not need to do it later in the pipeline. For segmentation, some critical parameters, you're going to want to put in your virion radius. So we actually, as you'll see later in practical, and I know I keep saying that, but I promise it'll be good. You'll be able to measure your virion radius in our interface, so you don't need to export images to ImageJ or something to do your measurements. You can do it right in the interface. You'll want to put a max number of virions per tomogram. So say you don't have a lot of virions, you only have like 5. If you put 25, you're probably going to get a lot of false positives. So you want to put that number a little bit above what you expect, but somewhere in range. That way you're not getting a crazy number of false positives to sort through on that segmentation tab. And the tolerance for virion radius during detection, this is similar to the size-based. So say my average virion radius is 500, but I've got some that are a little bigger, some that are a little smaller. I'm going to want to change my virion radius to accommodate that. Geometry-based, again, this is how we do the particles. So we have options for template-based particle picking on our geometry-based picking or uniform-based particle picking. So with template-based picking, you're going to input a template, and that will search along the virion surface that you've segmented for your template and detect where it is. Uniform-based is great for if you have virions that just have a lot of spike or gag or whatever protein you're looking for. They will just apply an even mesh around the surface of your virion and extract those points as particles. For particle detection, I've included critical parameters for the uniform. A note on the template is that the most critical thing for template-based searches is that you're picking a good template that's representative of the particle you're looking for in your sample. For the virion, for the uniform detection, you want to determine how fine you want that mesh to be. So that's your minimum distance between your spikes. Then also the size of the equatorial band to restrict your spike picking. So you could see that visual here. So that determines how wide here it's going to pick all the way around. The reason this is important is because in tomography, we know in reconstruction, we get missing wedge effects. you're trying to pick at the top here, it might not be as well segmented, or your particles might not be as good because of missing wedge effects. So equatorial band can be good there. All right. Neural network-based picking is our last particle picking feature. The first step in this is you're going to create a particle list using the preprocessing results visualization tab and that manual picking that we showed you a couple slides ago. Then you're going to use this list to train the neural network. After you've trained your neural network, you're going to run the trained model on your entire data set to get predictions on the entire data set. Training for our neural network does require a GPU. So this is one of the few areas of nextPYP where you do need a GPU for that neural network training. If you don't have a GPU, you could use a pre-trained model, but you are going to want to use a GPU for training if you're creating your own training set. When you're performing the neural network-based picking, you're going to want to get a minimum of 50 particles from 2 to 3 tomograms. And the reason you want to do multiple tomograms is because there can be differences between different tilt series that if you give your network more data to come from, it's going to do a better job of predicting on other data sets. This takes roughly 1 to 2 hours, and it is very epoch dependent on how many epochs you assign it. If you're not familiar with how neural networks work, it'll take 1 to 2 hours. That's the important bit. Predictions can be done using either CPUs or GPUs. So we estimate about 5 minutes per tilt on a CPU and 1 minute per tilt on a GPU. But the reason you might want to use CPU over a GPU would be because you can process more in parallel on a CPU, because generally, people have, say you have like hundreds of CPUs, but 5 or 6 GPUs. This is random numbers, but you're going to have a lot more CPUs than GPUs generally. And if you have 100 tilt series and you have to wait and do them sequentially on your GPU, it's still often going to be faster if you can process them in parallel using your CPUs. So you can do either, but if you have a lot of tilt series, it's probably going to be faster to use your CPUs for doing the predictions. Again, you still need a GPU to do the training. Some critical parameters for your neural network-based picking. Like we briefly mentioned, the number of epochs that you're using during your training is going to impact how long it takes and how well the model's trained. Bounding box is the box size for particles around your particle picks. So that's how much information you're giving the neural network to use around each of your particles for the training. And then lastly is the max number of particles per tomogram. So if I have a very sparsely populated tomogram, I'm going to want to set this number lower. And if I have a very heavily populated tomogram, I want to set this number higher. All right, so in this talk, we're also going to cover some special pre-processing features of the pre-processing block. So this is going to include a navigation bar for navigating around your results tab, the gallery for very easily visualizing some images from your tilt series, tilt filtering. So if you have a tilt series, but you have a couple images in that tilt series that are bad, you can exclude those. And then tilt series filtering. So if you have a large data set, but you have a couple of tilt series that are bad, you can exclude those. And then lastly, we're going to cover a little bit how parallel processing works in nextPYP and give you a visual graphic for how that works. So first are the navigation bars. This lower bar here is going to cover navigating for things within this tilt series. So here you'll be able to see your frame alignment results, your tilt series alignment results, your CTF results, and your reconstruction results. And again, these are just for, in this case, all for tilt series number 13 would be this bar. These bars up here, navigation bars, are more for things that are general to your data set. So this, you can click between your tilt series. The gallery we'll see in a second, but you can see an overview of a snapshot of each of your tilt series. The table, we'll also see that in a minute, but you can see a list of all your tilt series with some quick snapshots of data from each. And then the plots, you'll see that more in sessions, but you'll be able to see an overview of the data in plot format for your entire data processing. If you're someone who likes to just look at plots over quick like visual images, that's going to be a great tab for you, and it's a good summary of your data processing. So we're going to look first at the gallery, where the gallery tab personally, I think it's a great place to go for when I want to do particle picking. You can look here and say, I might see, oh, this, I know I can see some ribosomes on, so I'm going to go here to pick some ribosomes to train my set. If, say, I didn't want to use size space picking for this. Or I see that one looks nice and clear, and then this one looks, also can see some ribosomes, but it looks a little bit different. So maybe I'll click to that to just get some variety in which tilt series I'm using for my training. But when you click on this, it'll bring you to that tilt series page for that tilt series. So it's a really easy way to navigate throughout your data and have a visual reference for what you're navigating through. This is the exclude tilt function. So this is one tilt series, but say I know that my negative 60-degree tilt and my 60-degree tilt are both not looking so hot. I can choose to ignore them here. That way they're not used later in processing. And I don't need to go like into my cluster, delete specific images off the tilt, worry about them being used. I can exclude them in here, and we're not going to make you go through the terminal and manhandle your data. You can do it through the web interface, which is nice. And as you can filter individual tilts in a tilt series, you can also filter entire tilt series out of your data set. So this is done in the table page that we showed on that navbar earlier, but this gives you a table and you can click on each of these and see a summary of the data. So an overview of the tilt series, the 1D CTF profile and the 2D CTF profile are currently included here. If you were a user and you were thinking, oh, there's something else that I think would be amazing to have there, you should let us know on our GitHub. But we put this here and you can click through and we have easy keyboard commands, X or C to exclude or include a tilt series, which is really easy, but it's similar to the manual picking. You would name your filter here and then click save, and it would save that filter, and then you can apply it in your downstream refinement blocks. That way you're not processing tilt series and downstream refinement really time-heavy steps that are not containing good data. All right, so this is going to be a visual to demonstrate how you can process tilt series in parallel using nextPYP. So the first thing that's going to happen is, say I have 9 tilt series and I'm going to go ahead and launch my job, and that's going to put these 9 into the queue. And once they're in the queue, they're going to go over to the split jobs. And so now these 3 are running in parallel. Let's say for this example, I can only process 3 at a time. That's all the resources I have. But these are going to work and they're going to start processing while the other 6 sit in the queue. And then these are going to finish. And once they finish, they'll know if they either were successful in green here or failed in red. And I'm going to grab a new set of 3 to start running in the split job while these go and get evaluated by the merge. The merge is going to know that this one failed and these 2 were successful. So it's going to start to send the failed jobs back to the queue. So we'll see here, these jobs finished, some successful, some failed. The failed will populate back to the queue. Once the queue is completely done with the original jobs, it's going to put the failed jobs back in line to reprocess those. So now the failed jobs are back in line since all the other jobs were successfully completed, and they're going to go back to my split jobs, get completed, they all worked this time, and now we're done. This is a visual of what that'll look like in your jobs panel. So say I'm running a job, I launch it, goes to the split. The first time it goes, 4 of them are unsuccessful, and it's going to go back to the merge, and the merge will send those 4 back to the split jobs to try and run again, and this time they worked. So now all my data is complete, and we only allow it to do this once. That way, if there's something actually wrong with your process, it's not going to keep putting you in this loop endlessly, but it does give it another chance. Say something was wrong with a specific node, odds are when it gets resubmitted, it'll go to a different node, and you might get better luck this time. So in summary, we talked about pre-processing in nextPYP, and we're happy now because we can do it in an automated fashion and without having to navigate in and out of a bunch of things. So again, we can take our tilt series and do motion correction, tilt series alignment, CTF estimation, tomogram reconstruction, and particle picking all in our one pre-processing super block here. Once we're done, you then get a particle set, and we've shown these 3D here because that's typically how tomography particles are represented, but our particles are 2D projections that we're then going to use for constrained single particle tomography refinement, as you'll see in the next session. However, if you are just a die-hard fan of subvolume averaging and you want to go do that somewhere else and make us sad, we do have a feature where you can extract your subvolumes for refinement in other packages. So we do allow that if you do want to go do SVA elsewhere. We don't support it in nextPYP as it is more computationally expensive than our 2D projection refinement, but you'll hear more about refinement in the next session, and we will start to take questions now.
All right, thank you, Avi. There's actually several questions on the topic of selecting, actually removing bulb tilts. So I don't know if you want to say it's just a bit more about that, and particularly how it works. You know, like you, I guess, cross them out on the interface, and then after that you need to rerun the block. So maybe you should say a little bit about that.
Yeah, are they on bad tilts or bad tilt series?
Bad tilts.
Bad tilts. Okay. So yeah, so you'll get to that exclude tilts page after. So you'll have initially run your preprocessing block once, and then you can visualize your results in the block, and you'll see that exclude tilts option, and you'll check which ones you want to exclude. And then you'll have updated your block essentially. So once you've done that, you'll need to rerun it. Generally, the blocks will give you some kind of indication when things are no longer out of date. I think that may just be with the parameters though, rather than the exclude tilts feature. But once you've checked exclude tilts, yeah, you'll want to rerun the block. That way it'll apply that in your reconstruction.
The next question is somebody asking whether we support picking of filaments or tubular structures.
Filaments, I believe that's an upcoming feature in MyLo-PYP. Correct me if I'm wrong.
Yeah, that sounds right. Yeah.
Yeah. So I would say it's not currently in there unless you do the manual picking, but it's an automated version is coming soon.
Great. The next question is asking, can we repeat the pre-processing step using different parameters without having to rerun all stages? For example, if they wanted to try out like a different tomography reconstruction technique, can they reuse the same alignments? Or if they wanted to try like a different way of picking particles, can they reuse the same tomogram?
Yes. So your pre-processing block is only going to rerun things that are downstream of whatever you've changed. So the stream kind of being you start with your frame alignment, you do your tilt series alignment, your CTF estimation, reconstruction, particle picking. So anything that you change is only going to update things that are downstream. So if I want to change my reconstruction parameters, or say I don't like how iMod did it and I want to try RTOMO, if I change that, it's going to keep the alignments, the CTF estimation, and it's only going to rerun reconstruction and particle picking. Same if I want to change my particle picking method, it'll keep everything up to reconstruction and just change the particle picking. And we often do that. We usually visualize the reconstruction results and go look at the block before we do the particle picking. Especially because if you want to do manual picking or something, you're going to need a tomogram to pick on. But then when you rerun the block, it'll only do the particle picking and keep everything else.
Wait, the next one is, how many times does a job get rerun when it's marked as failed?
It'll only get sent back one time. So it'll try jobs a total of 2 times. Either it will succeed the first, or it'll fail the first and succeed the second, or it'll fail both times and then quit.
All right. So see, there's another question here that is related to being able to import particle coordinates from external packages like Dynamo. So is it possible to do that?
I may need to phone a friend to you on exactly what we allow import on, but I believe we do import. I think we can import things. I just don't know exactly what we all import.
Right. Yeah. So right now there are ways that this can be done, but it's not accessible or easily accessible from the graphical user interface. We are thinking about trying to make that easier because we I guess recognize that some users may be picking the particles elsewhere, and they may want to bring them back into nextPYP. So right now, I guess the easiest way is to, if you have like a 9-mode model with your particles, that you should be able to do, provided that you place them in the right directories within your project. But as far as Dynamo specifically, it will need to be some translation between the format that they use and the format that PYP uses. But if you can convert those XYZ coordinates to an nine-mode model, then you should be able to import those into an nextPYP. Okay. Let's see. So the next one is what CDF methods does the preprocessing support?
For CTF, we typically use CTF find 4 with a little bit of our own flavors on it. But that's our default, and I believe we support CTF plotter now, question mark?
No, I
was
think
that
it's
like
still the CTF find. It's based on CTF find 4.
CTF find 4, okay. Yeah.
All right, so we have time for a couple more questions, and let's see. So there is a question also regarding, bringing data back into nextPYP. The specific question is how easy it is to bring data at different steps. Like, for example, can I upload tomograms to try the neural network picking? And then can I export those particle positions as a star file?
I'm
Should I
not
try
sure.
to answer that?
Yeah, I'm not sure how easy that would be in the web interface. But
Right.
okay.
So yeah, I think this no, you can't really upload tomograms to nextPYP. One thing I can say that 3D reconstruction of tomograms and 3D series alignment, the entire pre-processing, all the operations in pre-processing, they're very routine, right? So it's really easy to just recreate those tomograms. You wouldn't need to, it should be pretty straightforward. And then at that point, you have the tomograms inside nextPYP, and then you'll be able to pick particles and run the neural network picker. If you wanted to get more involved, the neural network picker is kind of like a component that was added to nextPYP. So you could potentially go and try that out, outside of the web interface. You can just run the Python code that does the neural network picking, and then you'll be able to, get coordinates that you can export, as a star file or some other format.
Yeah, I would echo what Alberto said about it's the point of this pre-processing superblock is that it's so easy and fast to make your tomograms that even if you have a lot of tomograms that you would need to rerun, they're easy to rerun. the thing runs in 10 minutes for me for stuff. It's really fast and effective. Yeah.
Okay, there's another question related to the neural network picking. It said, how can I give nextPYP the particle list to train the neural network? Is there a detailed tutorial on that?
I don't think there's a detailed tutorial on importing your own list, if that's the question. If it's doing the manual list, that we will definitely be covering during the practical.
Yeah, I think this is referring the manual list within nextPYP.
Oh yeah, the manual list within PYP, yeah, is gonna do in the practical, so you'll see how that works. Yeah.
But yeah, so there will be, once you are ready to train, you will have a chance to choose which list of articles you want to use for training. So, but yeah, we'll demonstrate that tomorrow during the practical.
Yeah. Which will be recorded if you can't make it tomorrow. So yeah.
Okay, so we should probably do maybe 1 or 2 more questions. Okay, there's one here. It says CTF find 5 seems to work better for tomography. Can you please try to integrate that into nextPYP?
We can definitely look into it, and we appreciate suggestions. So yeah.
Right.
Sorry, short answer, but yeah.
Yeah. So maybe one last question. And this is regarding the geometry-based particle picking. So the question is the normal to the surface of the picked particles, is it used to initiate alignment later on, like 3D alignment?
Yes. So the part of the benefit to segmenting the virions is you get an initial direction for the particles to initiate alignment. Yeah. If you have more to elaborate on that, go for it. But yeah.
Yeah, so definitely yes. You know, you can definitely do that, and it will save you a lot of compute time because you'll already know roughly what the orientation should be. And I think in the case of the the particles that are on the surface of normal to the surface, then essentially you reduce the number of angular searches to just one in plane rotation, and then the other 2 you can refine later. But essentially that will make the whole process be significantly faster. I'm trying to look if there's like a short one that we could address very easily, because we have
2 minutes. Yeah.
Yeah. Okay, so one question is that is actually belongs to the pre-processing and that you can maybe comment on. Is there an easier way to define the frame pattern file names?
Yes, so the frame pattern file name is pretty customizable to what your group uses, which is part of why we have it in there. And then if you wanted to use your MDoc files instead of having information in your file name, you can check the MDoc file box. Like use read from MDoc files, the data. Your name needs to be specific enough that way tilts are all unique from each other for sure. But yeah, there's some flexibility in your naming pattern there, as long as your naming pattern in the pre-processing block is consistent with the naming pattern in your data.
Great, thank you, Abby. That's all the time we have for questions. So we're gonna move on